What is that?
Okay, where did that music come from? Very good, top of the class, excellent. It's a remix, but anyway. I was going through some of these points in some of the earlier presentations. I've done retired, I've done dogs, 200 papers, that's an easy one. I have 200 papers published in the peer-reviewed literature, all original research. More tomorrow. Okay, do aliens exist? Let's have a poll. Who thinks there's life out there? Show of hands. Good, not bad. Who doesn't think there's life out there? Show of hands. You're in the minority. And who didn't vote for whatever reason, apart from my wife over there who never votes? A few of you, thank you for voting this time, even though you didn't want to vote. Well, for those of you who have no idea whether there's life out there or not, I can assure you at the end of this presentation, you'll be none the wiser. All right, how did life evolve on planet Earth, and when did it? Well, our planet's about 4 billion years, and it is in the seas that things began. Our earliest fossil, there's an example of an early fossil shown here, 3.5 billion years ago. We don't find many of these because there's no hard structures in them. So to find a fossil of something that is completely soft is very rare. This is small, it's a microscopic fossil. They're multicellular or they're single cellular, and they're very simple creatures. Then what happened? Well, as time progressed, a great deal of time progressed, we start to see life. So the Cambrian explosion is when we start seeing a lot of life, and as you can see there, 500 million years ago. The one that you might be most familiar with is shown here, a trilobite. I'm sure you've all seen these, maybe actually in a fossil shop, or you've seen pictures of them. They were sea creatures, and the seas were teeming with life in ancient Earth. It's not till 400 million years ago that we start to find traces of life on land. And when you consider how old the planet is, this wasn't very long ago. But the conception is very simple. Miller looked at the atmosphere of primordial Earth. He simulated lightning strikes through this atmosphere and saw what happened to that atmosphere. Now, I know this is not as clear as it should be, but in the atmosphere here, I'll read it out to you, there's methane, ammonia, water, and nitrogen. I think that's nitrogen. It's a bit blurred to me. What's missing? There's no oxygen. And in fact, the early atmosphere of Earth had no oxygen. It came later. Anyway, sparking this in this reaction chamber, then condensing out the chemicals that had formed in the condenser here and looking at it in the water, and then recycling this and keeping doing it. What he found were amino acids were being formed, other more advanced chemicals, more complex chemicals were being formed, and these then could go on and react with themselves. And in fact, what we're in the stage that we're in here is a chemical evolution. The organic chemicals are coming together, they're reacting in the ocean, the unstable ones go away, the ones that are stable exist, they propagate, if you like, they're not living, but they will react with other molecules, and it gets more and more complex. Now this takes a very long time. So we've been to Mars. Here's the Viking lander. There's the sun. The sun is quite a bit smaller when you're standing on the surface of Mars because we're further away. So there's much less heat. Average temperature on the surface of Mars about minus 63 degrees centigrade. This is the surface of Mars. There's not much moving there, right? What we didn't find was that. Which film does that come from? John Carter. Yes, that's right. And those books, by the way, were sort of, the genesis of those books were the early observations from Lowell and other astronomers identifying canals which don't exist on the surface of Mars. Let's try and appreciate distances. So in astronomy, we measure things in light years, that is the distance light travels in 1 year. And that's a very large distance. This is the speed of light in SI units, 300,000 meters per second. This is a light year, then in meters, but let's just approximate. It's either 10 trillion kilometers or it's 6 trillion miles for 1 light year. This is 63,000 astronomical units. That is 63,000 times the distance of the Earth to the Sun. So light goes a very long way, very quickly. But it is still slow when it comes to astronomical distances because the distances are astronomical. That was a pun. Thank you. Okay. Pioneer, Voyager, they have been launched. They will take a long time to go 1 light year at their current speed. They will take 10,000 years to go 1 light year. Not very suitable for space exploration, either for us or somebody coming to visit. They really need to go about 10,000 times faster to be of any effect. But we do not have the technology for that right now. This is our closest neighbor. It is 4.2 light years away. In other words, at the speed of light, it takes 4.2 years to get to it. We cannot travel at the speed of light. We can't even travel at a fraction of the speed of the light at the moment, a significant fraction. There's another problem too. This comes out of Einstein's theory of relativity. If you could travel close to the speed of light, then there is such a thing known as time dilation. And people experience time differently at different speeds. Close to the speed of light, time goes slower. So, for example, if it took 2 years to travel 50 light years, then the crew have experienced a time of 2 years. But back on Earth, it's been 50 years. So just think about what would happen if you were away for 2 years and then came back 50 years later. Who's left? The next one is life periodically is destroyed and it re-emerges again. We know on our own planet there have been several mass extinctions. The most recent one, of course, is the dinosaurs. But there have been others before it. There's been several. So the next bullet, I want you very carefully to look at your neighbor. Because maybe they're already here. See if there's any strange scars down the side or behind the ears. Does anybody look a bit not human to you? Well, I know some of us don't seem human sometimes, but anyway. So anyway, that's one answer. And then finally there's the great filter. And the great filter really is just a catch-all that in fact that it is too difficult for civilization to arise to a point where they can do what they need to do, or that the time is too short for the length of that civilization to evolve to the point where they can do interstellar travel. All right, now we get to the Drake equation, 1961. And in 1961, they had no idea there were as many exoplanets as we know there are today. Frank Drake came up with this, and it is still controversial today, although work is still being done on it, as you'll see. And what Drake tried to do with this equation was get an idea for what's really going on, what are the chances. So, this is the Drake equation. I'll go through it. In 2010, an Italian, Claudio Marconi, extended the Drake equation using statistical parameters. This gives more, well, I'll say reliable, gives more reliable estimates of what these parameters mean. So using his values, we now have a little over 4,500 extraterrestrial civilizations. This is a probability curve, so probabilities are now assigned to the assumptions that are being fed into the equation. The range, however, is still from 0, so that is still a unique solution that we're alone in this galaxy, but it goes up to just under 16,000. If they are evenly spread apart, they're about 28,000 light years apart. 28,000 light years. Remember 28,000 light years. And you'll see why that's important in a second. For 75% of them, then, this is the range that they are away from us. They're anywhere from 13 2,500 to just under 4,000 light years away. And you can also remember 1,300 light years. Okay, so 28,000 light years and 1,300. This was published in an astronomy journal. That's the reference in 2011. Almost getting to the end. The wow signal. I said we hadn't found anything, but in fact we have. 1977, a brief signal came in on a radio telescope, and it was an enormous intensity. This is the intensity of the signal that came in. The person on duty at the time was so stunned, they wrote wow on the result. And that is why it is known as the wow signal. It only lasted a short time. It came in on the hydrogen line. The hydrogen line is fundamental to our universe. It is, yes, it's just fundamental. It's the simplest element. And if we were looking for something, that's where we would look. We would look on the hydrogen line. Where is it? Well, we're not quite sure. The resolution of that radio telescope wasn't so great. It's in the Tau Sagittae area. As you can see from the red bands there, there's some uncertainty to the position of where that signal came from. But at least we know in the general direction of sky where that signal came from. They listened and listened and listened. It wasn't repeated. They have no idea what it is. This is the radio telescope that heard it. There's the wow signal again. 1977, nothing's happened since. What was it? No idea. Oh, a little bit of fanciful now. Actually, people are thinking about this. Biologists are looking at our own planet. They're extrapolating and trying to figure out what aliens might look like. Here's some pictures. We'll see some more in a little video clip that I got. This large, massive creature here, for example, might be something you would find on a heavy, high-gravity planet. Obviously, you would not want to have spindly bones. On a high-gravity planet, you would be massive, you would need strength. This is an aerial beast. Actually, it's a flying whale. That would probably be on a very low-gravity planet to support that mass. This one you'll see in a minute. And that is a microbial creature, the mining system. This is a large crustacean that was dreamed up. And down under the water. This is a clip from a documentary called Aurelia. We have a few minutes for questions if anybody would like to so ask. Yes, I'll get back to you. Yes, sir. Are we likely to find wormholes? Are we likely to find wormholes? Well, if they're going to be anywhere, they're going to be around where black holes are. Unfortunately, one cannot enter a black hole and survive to tell the story. So right now, I don't think the answer's very favorable. Is carbon the only element that will form a chain? I'm glad you asked me that one. No, silicon will do that too. The problem with silicon, though, is most of its compounds will react with oxygen. So a silicon life form in an oxygen atmosphere just wouldn't happen. But silicon chemistry is nowhere near as rich as carbon chemistry. So right now, everything that we think would form life is based on carbon. What are my personal thoughts about microbial life, past, present on Mars? I see no reason why it could not have evolved there. The conditions were right. Just because we haven't found it yet doesn't mean it wasn't there. There's indications it was there, but we have no proof right now. So I'm optimistic. Yes. That was the intention of avoiding. Okay, thank you very much. You all need to go to the next event.
They don't need to.